Our research question is, what determines the lambda max during emission spectroscopy?
In emission spectroscopy, lambda max is the wavelength of the photon with the greatest intensity, or the wavelength where the most photons are produced. The wavelength of the photon is determined by the energy released during emission as electrons return to their ground state from their excited state.
During photon absorption, electrons are excited to higher energy states. So when energy is added to the system, the electron will move to a higher energy level. It is energetically unfavorable for an electron to remain at a higher energy level because the most stable state is the ground state. If an electron is at a higher energy state, the electrons are farther away from the nucleus, which results in the total energy being higher due to an increase in potential energy. The potential energy increases because there is more distance from the nucleus. Therefore, the attractive forces are lessened. In the ground state, the total energy of the system is lower, which is more favorable. In order for the electron to return to its most favorable state, the electron will drop back down, releasing the energy in the form of a photon. That photon has a specific wavelength that corresponds to a form of electromagnetic radiation.
Lambda max is determined by this specific wavelength. Each substance will have its own individualized lambda max, as each substance will require different amounts of energy to excite electrons to a different energy level. This is due to the differences between a molecule's composition that determines the likelihood of that molecule's electrons moving to a higher energy level. There are many different aspects of molecular composition that contribute to the likelihood of an electron moving to a higher energy level, including electron density, structure, geometry, shape, etc. One display of this principle is that available energy levels will vary amongst molecules. For example, a bromine molecule's electrons will occupy more energy levels than a fluorine molecule due to the fact that bromine has more electrons than fluorine. This means that if the same amount of energy is placed into the molecules, fluorine is more likely to absorb less energy, as fluorine's electrons have lower potential energy and thereby are more resistant to raising to higher energy levels.
Because each molecule will have intrinsic differences in its composition and structure from any other molecule, the lambda max during emission spectroscopy can be used to identify what the substance is that is emitting that photon. This means the statement that lambda max is determined by observed color is incorrect, which is backed up by in-lab evidence in which the 1-to-1 mix actually showed 2 peaks, indicating that these 2 peaks actually correlate to the lambda maxes of the 2 dyes.
This is similar to chemistry students and their lab assignment. The closer they are to the assignment, the more likely the assignment is to be completed on time, which is favorable to that student's lab grade. Think of this like the ground state of an electron. It is favorable to the electron to remain as close as possible to the nucleus, because this requires the least amount of energy. It requires energy to increase the distance between the student and the assignment, just as it requires energy to increase distance between an electron and the nucleus. This is what happens when an electron is excited to a higher energy level. This is unfavorable, though, in both cases. In the case of the student, it is unfavorable to the student's grade to maintain this distance from their assignment, and eventually the student must return to their assignment. And this decreasing of distance causes an emission of caffeine products and cortisone levels. The same occurs in electrons. It is energetically unfavorable to remain at a higher energy level, and as the electron comes down to a lower energy level, energy is released in the form of a photon.